Exponential equations are of two types. The first type, where both sides can be written with the same base. If that's a possibility, our goal is to write both sides with the same base and then use one-to-one property of exponential functions, which means if two output values are equal, then two input values are also equal. The corresponding input values are equal. The second type of exponential equations are where both sides cannot be expressed with the same base. In that case, we will isolate the exponentiated term and then take log to the base 10 or natural log or log to any base b on both sides and then solve. Let's look at type 1 problems first. 3 to the power x equals 81. We can clearly express both sides here with the same base. 81 can be written as, I can now use the right pen. So a to the power x equals 3 to the 4th power. 81 is 3 to the 4th power because 3 times 3 times 3 times 3 is 81. So now we're going to use one-to-one property, which means if two output values are equal, then two input values are also equal. So x has to equal 4. Next example, 5 to the power 7 minus x. 125 can be written as 5 to the 3rd power. So if two input values are equal, if two output values are equal, the corresponding input values also have to be equal. So x has to equal 7 minus 3, which is 4. Next example, 1/2 raised to the 4y power equal to 16. We can express both sides with the same base here. We can express 1/2. We can express both sides with the power 2 here. 1/2 is same thing as 2 to the power -1, and 2 to the 4th power is 16. So on the left-hand side, 2 to the power -4y, right-hand side, 2 to the 4th power. -4y has to equal 4. If two output values are equal, two input values are also going to be equal. So we get y is equal to -1. Domain of exponential functions is all real numbers, so there's no domain restriction. We don't have to worry about any domain restrictions in case of exponential equations or exponential functions. Next example, we have 16 to the power x minus 1 equals 8 to the power 2x. We can express both sides with either, actually only with the power 2. 2 to the 4th power is 16 and 2 to the 3rd power is 8. Now, these two exponents are going to multiply based on the rules of exponents. 2 to the power 4x, don't forget to distribute the 4 into entire outer exponent, is equal to 2 to the power 6x. Now, if two input values are equal, if two output values are equal, two input values are also going to be equal. So 4x minus 4 equals 6x. Let's go ahead and isolate the x here. Subtract 4x from both sides. X comes out to be -2. So x in this case is -2, and that's going to be the value of x that makes both left and right hand side equal. Example number 5, e to the power 5x minus 1 equals e to the power x squared plus 3. So using one-to-one property, again, it's helpful if we actually include using one-to-one property. We're not canceling the bases. It's not okay to cancel the bases on both sides, but we are using one-to-one property, which means if two output values are equal, then two input values are also equal. So 5x minus 1 is going to equal x squared plus 3. Let's bring all the terms on one side and factor it. Two numbers multiplying to -4. Actually, this is going to be, if I take everything to right hand side, it's going to be plus 4. X minus 4, x minus 1 will be the factors. So x equals 1 and 4. There's two solutions in this case, 1 and 4. Now we're going to look at some type 2 problems where both sides cannot be expressed with the same base. In that case, our goal is to get exponentiated term all by itself and then take log on both sides, either natural log or common log or log to any base b on both sides. Okay, so first example, very simple. we cannot write 5 as 3 to some power. So we're going to go ahead and take natural log on both sides. And we will always leave our answer in the exact form. But if we want to get a decimal form, we can use calculator when solving exponential equations. Now, exponential functions have a special property that the exponent can become coefficient in the front, the power rule. So it would become x times natural log of 3 equals natural log of 5. X would be equal to natural log of 5 divided by natural log of 3. And that's the value of x that's going to make this equation left and right hand side equal to each other. Example number 2, we already have the exponentiated term alone on one side. So we're going to go ahead and take natural log on both sides. Again, you don't have to take natural log. You can take common log. You can actually also take log to the base 4 in this case. That's going to make your life easier as well. But I'm going to stick with the natural log. So the exponent comes in the front. Natural log of 4 equals natural log of 71. 3x plus 2 comes out to be natural log of 71 divided by natural log of 4. From here, when solving for x, we can get x equals natural log of 71 over natural log of 4 minus 2 divided by 3, which can be simplified a little further. We can write it as x equals 3 natural log of 4 natural log of 71 minus 2 natural log of 4. Let me use more space. This can be simplified to 3. In the denominator, I would have 3 natural log of 4. Numerator would be natural log of 71 minus 2 natural log of 4. And that's going to be our answer, the x value that makes the left and right hand side equal. Again, we're leaving them in the exact form, but we can find the estimated value or approximate value using the calculator as well. E to the power 2x equals 8 times e to the power 2x equals 20. So first step is to get exponentiated term alone. Divide both sides with 8, which turns out to be 10 over 4. E to the power 2x equals 10 over 4. Go ahead and take natural log on both sides. And that would be 2x times natural log of e equals natural log of 10 over 4. Now, natural log of e is equal to 1, one of the properties of logs. So 2x equals natural log of 10 over 4. And to isolate the x, we will get 1/2 natural log of 10 over 4. And that's what x is equal to. Example number 4 looks like it's a quadratic equation in e to the power x. So how do we solve a quadratic equation in e to the power x? We can let e to the power x as u. I'm going to erase this problem to give me more space to do problem number 4. So we can let e to the power x as u or t, whatever we want, doesn't matter. We can call it t. So this new equation becomes t squared minus t minus 6 equal to 0. Two numbers multiplying to -6, adding up to -1 are -3 and +2. So I get t equals 2, t equals negative, t equals 3, and t equals -2. So we're going to replace t by e to the power x. E to the power x equals 3. E to the power x equals -2. Now, exponential functions are never negative. Exponential functions, if you recall, they never go below x-axis. They actually never even touch the x-axis. The exponential functions are never negative. The y value is never going to be negative for any exponential function. So this piece is going to have no solution. But the other piece, we can go ahead and take natural log on both sides. X will be equal to natural log of 3. That's the only solution here. Number 5. First step is to isolate the exponential equation, exponential term, the term that is exponentiated, sorry, the term that is exponentiated. So we want to get that term by itself. So we're going to go ahead and subtract 35 minus 8. That would be 27. 3 times 2 to the power x equals 27. Go ahead and divide both sides with 3 so that we have our exponential term all by itself. So we are left with an equation 2 to the power x equals 9. At this point, we are going to go ahead and take log. Again, we could take log to the base 2, log to the base 10. All of those are okay. So I'm going to show you all three here. So if I take natural log 2 to the power x, natural log of n, so I'm going to be left with x times natural log of 2 equals natural log of 9, which leaves me with x equals natural log of 9 divided by natural log of 2. What if at this step I decided to take log to the base 2 on both sides? Log to the base 2 of 2 to the power x equals log to the base 2 of 9, which is going to leave me with x equals log to the base 2 of 9. And using change of the base formula, these two are equivalent. And we could also do common log, which is log to the base 10 on both sides. In that case, it would have become log to the base 10 for 2 to the power x is log of 9. So x log of 2 is going to be log of 9. X would be equal to log of 9 divided by log of 2. Again, which is the same thing as the previous two forms. So all of them are equivalent using change of base formula. Let's look at example number 6 now. We have example number 6. We have an addition involved in there. So we got to be clever with this problem because it seems like with the plus in there is causing some issues for me. So I'm going to go ahead and try to break it as 3 to the power x times 3 to the power third, because the exponents will actually end up adding like we had. So I'm writing it as two separate product of two terms instead of writing it as a single term. Plus 3 to the power x equals 84. Let's pull out 3 to the power x. 3 to the power 3 plus 1. So we factored out the 3 to the power x. 3 to the power 3 is 27. 27 plus 1 is 28. Now we can divide both sides with 28. 84 divided by 28. Okay, at this point, we can simplify, divide both of them with the 4. Divide 84 with the 4 and 24 with the 4. 28 with the 4. So 28 divided by 4 is 7. 84 divided by 4 would be 21, which is going to be a 3. Let's see. 21, 7, and all right. So we have 3 to the power x is equal to 3 to the power 1. X would be equal to 1 in this case. And that's all for this problem, and we are done with looking at exponential equations. So we saw two kinds of problems. Ones where the both sides have the same bases or can be expressed using the same bases, and the second type where we cannot express both sides using the same base.